Welcome back to the online course on analog integrated circuits. In the last class, we have learned what is phase locked loop, how it operates, and the terms capture range and locking range. In today's class, we are going to discuss one of the PLL integrated circuit, that is IC 565. Also, we will learn some of the applications of PLL in detail. Here, these are the questions asked in the KTU B.Tech examination so far. All are direct questions like explain operation of PLL, explain any two applications of PLL, etc. Let's start with PLL IC 565. IC 565 is the most commonly used phase locked loop IC. This IC is available as a 14-pin dual in-line package. Here is the pin diagram of IC 565. In this IC, out of 14 pins, only 10 pins are utilized for the operation of PLL. Here the pin numbers 1 to 10 are those pins, and the functions of each pin can guess from the labels of those pins. Remaining 4 pins are labeled with NC, which means no connection. Let's look at some of the characteristics of IC 565. Its operating frequency ranges from 0.001 Hz to 500 kHz, and operating voltage range is plus or minus 6 volt to plus or minus 12 volt. Input impedance of IC 565 is typically 10 kilo ohm, and its output sink current and source current are 1 milliampere and 10 milliampere respectively. There will be a drift in VCO center frequency of 300 ppm per degree Celsius and 1.5% per unit supply voltage. The input voltage level required for the tracking is RMS voltage of minimum 10 mV and maximum of 3 volt peak to peak. And bandwidth adjustment range will be plus or minus 60%. Here is the block diagram of IC 565. This PLL system consists of a phase detector or comparator, a voltage controlled oscillator, an amplifier, and an RC combination forming low pass filter circuit. The input signals are fed to the phase detector through pin numbers 2 and 3 in differential mode. The DC level at these two pins are seen, and the DC resistance seen from those two pins are equal. Hence, the signal can be applied through direct coupling. By shorting pins 4 and 5, output of VCO can be applied back to the phase detector or comparator. The output of this phase comparator is connected to this amplifier, and the output of this amplifier will be available at pin number 6 and 7. There is a resistor 3.6 kilo ohm connected between pin 7 and output of the amplifier, and a capacitor C2 connected between pin 7 and pin 10 forms a low pass filter. The capacitor C2 should be large enough so as to eliminate the variations in the demodulated output and stabilize the VCO frequency. Voltage available at pin 7 is connected internally to VCO as a control voltage. At pin 6, a reference voltage nominally equal to the voltage available at pin 7, which is allowing both differential stages to be biased. The center frequency of the PLL is determined by the free running frequency of the VCO, which is equal to 1.2 divided by 4 into R1 C1, where R1 and C1 are external resistor and capacitor connected to pin 8 and 9 respectively. The free running frequency F out of the VCO can be adjusted to be at the center of the input frequency range by controlling the value of R1 and C1. The resistor R1 must have a value between 2 and 20 kilo ohm, and the capacitor C1 may have any value. And the log range of PLL is given as FL is equal to plus or minus 8 into F out divided by V heads, where V is equal to V plus minus V minus, and capture range Fc is equal to Fl divided by 2 pi into 3.6 into 10 raised to 3 into C2 whole raised to half. The log range usually increases with increase in input voltage but falls with increase in supply voltage. Let's move on to the applications of PLL. There are many applications for PLL circuit, especially in communication systems like AM detection, FM detection, frequency multiplication or division, and frequency synthesizer. Let's start with AM demodulation or detection using PLL. Here, the circuit of an AM demodulator which utilizes the PLL. In this circuit, PLL is locked to the frequency which is equal to the carrier frequency of the modulated signal, that is F out is equal to Fc. Under the locked condition, VCO output or PLL output is always 90° out of phase with respect to the incoming signal. So, the modulated signal is passed through a phase shifter which shifts the incoming signal by 90° and hence it makes the signal is in phase with PLL output. This phase shifted signal and the carrier signal, which is locally generated using PLL, are fed to the multiplier or a phase detector. Output of the multiplier contains the signal having frequency Fin minus F out and Fin plus F out, where Fin is the incoming signal frequency and F out is the PLL locked frequency. Here, the modulated signal will contain the frequencies Fc, Fc plus Fm and Fc minus Fm, and assume this AM signal is a suppressed carrier signal, hence the signal will only have Fc plus Fm and Fc minus Fm. For simplicity, consider only one signal. Let's assume Fin is equal to Fc plus Fm. Hence, the multiplier output will contain the signals having frequencies Fc plus Fm plus Fc, which is equal to 2Fc plus Fm, and Fc plus Fm minus Fc, which is equal to Fm. Then the low pass filter connected at the output of the multiplier rejects the high frequency components. In this case, it is 2Fc plus Fm. Hence, we will get the demodulated output, which is the message signal of having frequency Fm. This is how an AM demodulator using PLL works. This system has an advantage, that is, it exhibits a high degree of selectivity and noise immunity over the conventional AM demodulator. So let me stop here today. We can continue with some more applications in the next class. Okay, thank you.